Recording in progress.
Hey, this is Sai Varapalli. I'm going to present my understanding of the solution of assignment 2 here. So initially we are asked to load the necessary libraries, and then we are asked to load the diabetes data and set the return XY as true, which going to return two arrays. And then the diabetes data from the labels, we're going to convert the numerical labels into a category label. So what we're going to do here is we're going to take the average of the labels, average of the diabetes Y. I mean, like we're going to store labels in diabetes Y here. And then once we find the average, and then we are going to compare each label with the average. So if the label is greater than the average value, then we're going to assign it as 1. And then if it is less than the average value, then we're going to assign it as -1. So getting into the code, so we imported all the libraries that we're going to need, and then we imported the diabetes data set here. And then we set the return XY as true, which is going to return a tuple with features and labels. So we are storing the features in diabetes X and the labels in diabetes Y. So then we are just printing the shapes of diabetes features and labels, and also the labels. So here we see there are like 442 data set points with 10 features for each data set point, and then 442 labels for each data set. So here we could see the numerical labels. So then now we're gonna do the average. So we are using np.mean to find the average. And then once we get the average value, we're gonna assign label 1 for the assign value of 1 for the label, which is greater than the average, and -1 for the labels, which is less than the average. So using np.array and then comparing it with the array like I greater than y, mean if it's greater, it's going to get 1. If it is less, then it's going to get -1. So once we do that, we're going to store all the values in y binary. So as we can see, the average value we got here is 152.13, and then so this was labels, initial labels, and based upon that, in comparison with the average value, then we assigned 1 and -1 for each label and stored in y binary. So in the exercise 1 here, what we're going to do is now we got the samples. I mean, like now we got the features and the labels. So now we're going to split the data into 3 sections. So 60% of the data into the training section, 20% of the data into the test section, and another 20% of the data into validation section. So we're going to need train, test, validation library that we already imported initially. So once so we're going to perform the split here. So I got xtrain, xtemp, ytrain, ytemp, and train test split, and we are splitting the features and labels into. So here I need the training set as 60% and the other set to be 40%. So I'm putting test size as 0.4 and shuffle true. So it's just going to shuffle the values, and then the random state 42 with just make sure like if someone else is using the same code, when they're going to get the same samples, same split data. So once we run this code, 60% of the data would store into training set, and then the remaining 40% would go into temp. And then we are going to use the same function again to split this 40% of the remaining samples into 50% each, like 20% would go to the validation samples, and then the other 20% to the testing samples. So to do that, again, we implemented xval, xtest, yval, ytest equals to train test split. So we're going to split the remaining samples, which are in xtemp and ytemp, into 50% each for validation and test. And once we do that, we're going to print the shapes of the training, validation, and test sets. So as we can see here from the 442 data points, so features and those features, they're split into 60% went into, which is 265 went into training set, and the remaining 178 data is split into validation and test set here. So once we do that, then the next step was we're going to import SGD classifier, which is stochastic gradient descent classifier. So we're going to train our linear model using SGD. So to do that, we're going to import the SGD classifier that we already did initially. We're gonna loaded the SGD classifier library already. So now we're gonna use the training samples that we had to train the model. So once we train the model, we're gonna extract the coefficient and intercept of the fitted line. I mean, like the line that separates the labels. So we are doing that. So we are printing out the shapes for coefficient and the intercept. So I just also printed out the curve and transport. Just testing out some other code. Okay. So once we do that, we're gonna get the sizes of the coefficient and the intercept. In the exercise 2, what we are asked is compute the prediction and the accuracy of the model that we just tried. So we could either, I mean, like there are two ways. Either we could just go theoretical, like using the equation, we can calculate the prediction and accuracy based upon the equations, or we could just use the inbuilt functions .predict or .score to calculate the predict and accuracy. So what we're gonna do here is we're gonna implement both the systems and then compare the results. So first we are gonna implement the theoretical part where my result, so once I give the examples and then the coefficient and the intercept, so I'm defining a compute prediction function here. We are defining a compute prediction function here. So what this function does is once it gets the features and the coefficient and the intercept, it's going to implement it's going to implement a function like y equals to mx plus c function. So it's going to multiply the features with the coefficient of transpose and then add the intercept. And then for whatever the value which is greater than 0, it's going to assign a label 1. And for whatever the value which is less than 0, it's going to assign a label -1. And then it's going to reshape the data. And then it's going to return the result. And then same for the accuracy. So once you get the prediction value here and the actual value, so we're defining the function for accuracy here. So once we know the predictions and then the actual values, so how do you compare, how do you calculate the accuracy? You're going to divide, how well your program performed, what are your predictions by your total samples. So that's what we're doing here. So we are storing agreement equals to predict equals to actual. So whenever the predictor value is equal to actual value, it's going to store, it's going to add to the agreement. So then we're going to sum up the total values in agreement and then divide it by pred.shape of 0. So here pred.shape would give the shape of the predictor value, and then shape square brackets of 0 will give you the number of rows in predictor results. So what exactly we're doing is, so we are exactly from the first statement, we get the total number of predictions that were predicted 100%, whatever the predictions that are equal to actual is stored in one in agreement, and then we're going to divide it by total number of samples. So that way we're going to calculate how many samples it predicted correctly divided by total number of samples will give you the accuracy. So that's what we are implementing here. So once we calculate the accuracy, it's going to return the accuracy. So we define two functions here. So now from the so from the samples that we had, we're going to calculate the predictions for the training sample, predictions for the validation samples, and then predictions for the testing samples. So we perform the prediction function here, and then we got the predicted values for the train, validation, and test. And then for these values, we're going to calculate the accuracy. So to do that, then we are sending the predicted values and then the actual values to the compute accuracy function that we defined. So once we do that, we got the accuracy for training, validation, and test samples. So here, as we see, the accuracy is 76.2%, 78.4%, and 73.03%. for train validation test sets. So now what we're going to do is we're going to implement the inbuilt accuracy calculation function to see if the way we perform the predict and accuracy matches with the inbuilt functions. So simply we're just going to implement the clf.score. Score is the inbuilt function to calculate the accuracy. So once we do that, as we can see here, we got the values of 0.762, I mean, which is 76.22%, 78.4%, and 73.03% for train validation test samples. So those match with the other, the theoretical ones, I mean, the one we implemented. All right, so in the second section of it here, in the linear regression section for assignment 2, so what we're gonna do is here, we're gonna generate a regression samples randomly. We're just going to generate some regression samples using the code provided. XY, like make regression samples, features, noise. We're going to specify everything. And then once we do that, we're going to visualize the samples that we generated. So in order to generate the regression samples, we're going to import the make regression library. And to plot the figure or to visualize the data, we're going to import the matplotlib.pyplot as PLT. So once we do that using the code provided, we are going to generate the sample. So as the feature is going to go into X and the label is going to go into Y. So once we got that, we are setting the figure as 10:6 ratio in 10:6 ratio, and then dots per inch as 80. And then we are setting the label as X, Y, X-axis as X, Y-axis as Y, and the title as training data. And then once we plot that, I mean, we are also setting the legend, which gonna give us. So once we run this code, as we can see, these were the 100 samples. So here we asked for 100 samples. So these were the 100 samples that was generated by the code that we implemented. So now what we're gonna do is we're gonna perform the gradient descent function here. So what exactly the gradient descent does is it's an kind of optimization function. So we're going to implement the gradient descent function here. So as we can see here from the pseudocode here, we're going to initialize the slopes, and then for iterations 1 to the total number of iterations, we're going to calculate the slope and intercept. So for gradient descent, it's going to take features, labels, the initial slope, initial intercept, and we're going to set the learning rate, and also the number of iterations. And then to perform the iterations, the gradient descent function, we are setting the gradient descent function here, and then the gradient descent function will call for gradient one step for the number of iterations we asked for. So in the gradient one step function, it's going to take features, labels, and the slope, the intercept, the initial, which are the initial slope and intercept values that we specified, and then the learning rate, which we're going to specify. And then using those values, it's going to implement the slope gradient. So here, it's going to run a for loop for I in the range of n, where n will be the length of y, which means for the number of total labels in y. So it's going to run for each data point or each label. So for each step, it's going to calculate the slope gradient. So by implementing the function sigma here, minus 1 by n, which is where n is the length of y, and then for each element of feature, which is x, and then multiplied by y minus mx plus c, which is like, y label minus the initial slope, and then the slope multiplied by the feature, and then the intercept. So each time when the iteration does is, here we see slope gradient is plus equals to the code. So what exactly it does is every time when the operation here, what it does is it adds the value on the right, which is the value that was got from the right code, adds to the left and stores in the slope gradient. And it will, so same thing we're gonna do for the intercept gradient. So once we perform that, we're gonna, based upon the learning rate provided, we're gonna calculate the slope and the intercept and store it into the new slope and new intercept. Here we use new slope equals to slope minus whatever the learning rate we specified, multiplied by the slope gradient that was calculated. So that will be stored into the new slope, and then same for the intercept, it's going to store in the new intercept. So once we perform this function, it's gonna, so once we perform the gradient descent function, it's gonna call for gradient one-step function, and then the gradient one-step function will return you the slope and intercept values. So once we do that, here we were giving the learning rate as 0.01, and then the initial slope as 0, initial intercept as 0, and then the number of iterations as 1000. So we are setting up same the learning rate as 0.01, 0, intercept 0, and number of iterations and as 1000. And then we are gonna implement the grade descent function, which we defined earlier here. So once we do that, the calculated slope, I mean the new slope and the new intercept values will be stored into the slope and intercept. So here what we're gonna do is we're gonna plot the data. We're gonna visualize the data. So we're gonna visualize the data here. So and then based upon the slope and the intercept values that we got here, we're gonna visualize the fitted line too. So to do that, first we are first we are plotting the samples, the generated samples, the 100 generated samples that we generated earlier. And then we are setting up the labels for X and Y axes. And then for the fitted line, as we see here, our fitted line is in the form of, any straight line can be is represented as Y equals mx plus c here. So here the slope is the calculated slope, and then the X will be the feature, X, and then the intercept is the one we got from here, and then we are specifying the color of the fitted line as red, and then the label as fitted line. So once we do that, as we can see here, using the gradient descent function, the calculated using the slope and intercept. So this is the fitted line that we got, and these are the samples that we generated. Thank you.